In this example, Max is building a ramp that's 1 meter long up to a doorway that's a half a meter off the ground. And we want to know what angle the ramp makes with the ground. Okay, so let's just sketch a little picture. So we have this ramp. It's going up to, it's 1 meter long, and it's going up to a doorway that's a half a meter off the ground. Okay, and we want to know what's this angle. What's the angle that the ramp makes with the ground? Now this one you can see easily that this corresponds to, we're going to use our unit circle again. And we don't even have to scale this. We don't even have to scale this up or down, right? Because the ramp is 1 meter long and the radius of our unit circle is one unit, whatever it happens to be. So so we can just see that this is the triangle right here on our unit circle with the radius of 1, right? And it has 1/2 is the distance above the x-axis. And we know that one, right? We know this angle. We know this angle is 30 degrees, right? Or pi over 6, right? Because what we're given by knowing that this this ramp is going up to a point a half meter above the ground, but they're giving us the sine value, right? That's the y value of this point. So this is the point, whatever the x value is, and that happens to be square root 3 over 2, comma 1/2. 1/2 is the y value. So what we're given is the sine. So we know that the sine of theta is equal to 1/2 based on the information we're given. And we can introduce another new function. We can introduce the inverse sine. The inverse sine would take the sine value. Sorry, whoops. Let me back up here. It's going to tell us the angle given a sine value. So we could use the sine inverse of 1/2 will give us the angle that we're looking for. Now you can plug that in your calculator. You've got an inverse sine on your calculator. Or you could just use the unit circle. And we know that that angle had to be 30 degrees. Or pi over 6, right? So there we go. So there's a useful, an example where the inverse, these inverse trig functions come in handy. So let's take a look at the sine and the inverse sine. Now this is very similar to the cosine, right? So I just did the same thing as I did in my cosine example. Graph the sine function, y equals sine of theta, right? So this is y and this is theta. Okay, and I swapped the axes, right? So in this one, I've just taken the same image. It's exactly the same image. I've just flipped it in a couple different directions. And so this becomes the theta axis, and this is the y-axis, right? So with the inverse sine, we're putting in a sine value and trying to get an angle out. But we have the same problem, right? If I look at a sine value of 1/2, right? I have more than one angle that has that sine value, right? In fact, if I let this sine function go on and on forever, I've got an infinite number of angles that have that same sine value. But in order to be a function, every input has to have a unique output, right? And so we're going to remedy that problem by, again, restricting the range. So, but in this case, again, we want to be able to put in any value for sine between 1 and -1, right? Because sine only varies between 1 and -1. So we want to choose an interval here that covers all of the sine values possible. If we choose the same range that we did for cosine, which was between 0 and pi, you can see that, well, we have a problem. We're not going to have, if we use that as our range, we don't have any negative values for sine, and we wouldn't be able to figure that out. So we're not going to use that range. We got to use a different range that covers all of the possible sine values that we would possibly want to find the angle corresponding to. So we're actually going to restrict this to a different range. We're going to restrict it to this range so that the output is always between minus pi over 2 and pi over 2. Okay? So that's the key thing with the inverse sine. The range is restricted to between minus pi over 2 and positive pi over 2. Okay? We're always going to get an angle in that range. If we have to always think about when we're using the inverse sine to solve actual problems, we have to always then think that that range makes sense for the particular problem that I'm dealing with, because you might need to then take that angle and transform it to a different angle just based on whatever your problem is. But when you put a sine value into your calculator and hit inverse sine, it's going to give you an angle in that range. All right, so let's summarize what we know here about the inverse sine. And again, it can also be called the arc sine, okay? Because the notation is sort of confusing. This is what we're going to use primarily in this class, is the inverse sine with this little superscript -1, which indicates the inverse, okay? But it's not an exponent. It is not an exponent. So the inverse sine, again, gives you an angle. It always gives you the angle that corresponds to a sine value. You put in a sine value, you get an angle out. And that angle is always going to be between minus pi over 2 and positive pi over 2. Okay? So this is just restating this in a little more formal way. And again, the range of the inverse sine is always between minus pi over 2 and pi over 2. Okay? I'm really emphasizing this a lot. All right. The domain, the input, is always going to be a sine value, and sine can vary between -1 and +1. Okay. So that's all of the possible values for sine, because sine just oscillates between 1 and -1. But for the inverse sine, the domain is restricted to between minus pi over 2 and pi over 2. Okay, the range is the output. That's our angle that we're going to get out. All right, I will meet you in the next example.